A big thank you to the Talk Python team who sponsor this episode of the podcast. If you want to get better at Python, now is an excellent time to take an online course. Whether you are just learning Python to delve into great topics like artificial intelligence, or you need to go deep into things like APIs and async, my friends at Talk Python Training have a top-notch course for you. Visit talkpython.fm/mind to find your next level and get a 10% discount. Also a big thank you to all my Patreons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast. In this podcast we cover topics such as engineering, artificial intelligence, neuroscience and other interesting topics to educate, inspire and engineer people's minds all around the world. I'm your host Joseph, and in today's episode I welcome Jannik Zürn. Jannik is pursuing a Ph.D. in Robotics and Artificial Intelligence at the University of Freiburg in Germany. In his research, he aims at improving robot perception using unsupervised and self-supervised learning techniques. In his previous studies and his master's thesis, he focused on applying deep learning for problems in computational fluid dynamics. In this episode, Jannik will talk about how deep learning can be used for computational fluid dynamics, how to overcome obstacles when setting up the problem, and also what bottlenecks Jannik faced during his investigations. We will also talk about robotics and what Jannik thinks about artificial general intelligence and what he would ask such a system. And now, ladies and gentlemen, here's my discussion with Jannik Zürn. So, Jannik, welcome to my podcast.
Thank you for having me.
Yeah. So to get started, give us an introduction to yourself, what you do, because we started studying together.
Yes.
And now you're doing something different. Maybe let us know what you do and what you work on.
Yeah, so maybe some of your listeners might know that you studied mechanical engineering at the KIT in Karlsruhe, and so did I. And I actually think we started in the same year. Starting from then, we might have taken some different paths. So during my studies, I mostly concentrated on robotics and also on computational mechanics, including CFD. So that's maybe one more similarity in our interests. And after graduating, I started doing a PhD in Freiburg in a robotics lab, where I'm right now mostly concentrating on unsupervised and self-supervised learning in the context of robotics.
So that's super cool, Jannik. I also know that you worked on a thesis which involved fluid flow as well as deep learning. Can you go a little bit into depth?
Yeah, sure. So the basic idea was, well, since my personal interests lie both in computational fluid dynamics and also in machine learning, I was very lucky to find a thesis topic and a thesis advisor at the KIT that basically combines both of these interests. So the thesis is called basically a data-driven approach to computational fluid dynamics. And maybe the basic idea is to train a neural network to predict fluid flow in different settings, basically. So what you would have is you have your typical simulation setup that involves maybe a two-dimensional or three-dimensional computational domain. And with your machine learning approach, with your neural network, you try to predict how the fluid flows around and through the obstacles or anything that you might put into your simulation domain. And the way we try to do this is we first started simulating a lot of different cases. So we used OpenFOAM for this approach. So we basically wrote a script that generates us random geometries and try to simulate them, simulate the fluid flow around and through the polygons as detailed as possible, and use this as training data for a neural net. And in this case, we used a fully convolutional neural network, which basically allows us to put in the geometry of the stuff that we want to simulate using our neural network, and also the final simulation result, which is a flow field, basically containing all the vectors for all the different locations in the input geometry and the velocities of the fluid that are present at these points. And this can be used to train a neural network on both the input geometries and also the output, and minimize the error that the neural network does when it tries to predict how the fluid flows around certain kinds of obstacles.
Got it. How big was the highest error you measured at the end?
So we had different kinds of error measurements. Maybe like as a small tangent, basically this whole field is kind of new. So there is not a lot of literature going on. It started recently with a couple of publications that try to cover these grounds. But as I said, there are like not too many papers on this topic, which makes it on one hand super cool because it's kind of new and it's, you know, like in the Wild West, you can do like you can try out many things and you never know what's going to work or not. In the other, like the downside is basically that you have to kind of invent a lot of stuff as you go along. And also in the case of measuring errors, there are obviously many ways that you could try to measure them. So one way would be to, for instance, to find a scalar value that you can generate from the fluid flow that you predicted with your neural network. For instance, take in the context of, I don't know, aircraft simulation or a car simulation, anything, the direct value, which is basically saying, okay, how much of an obstacle is your thing that you try to simulate, depending on its shape and the fluid properties, obviously. And you can get these values from any kind of simulation software that you want. And you can also get these values from the final fluid flow that you get with the approach that we used in this thesis. And so this direct value might be one way to measure the error between between the ground truth, which is what the simulation says, and the prediction, which is what the neural network says. And depending on how complex your geometry is, you can get pretty close in terms of this direct value, how good the prediction is. It's about more or less 10 plus minus 10%, I would say, in most cases. But also as a disclaimer, we focused on in this work only on pretty simple geometries. So we tried, I don't know, random polygons and also like triangles, circles, stuff like that. So super simple shapes that are easy to generate and easy to simulate as well. So obviously, because of the nonlinearity of all the partial differential equations involved, it's super hard to generalize from simple shapes to more complicated shapes. So one interesting way to continue in the future would, for instance, be to start using much more data that we used in this work and see how well the network generalizes to these more complex shapes. Because the more complex your shapes get, the more complex the fluid flow gets, and also the more training data the network needs to see in order to be able to tell, okay, how well does, in order to tell, okay, how does the fluid actually flow around and through those obstacles that we try to put into our simulation domain.
Got it, makes sense. Before we go to the step-by-step on how you did it actually, I wanted to ask the difference. So the error that you mentioned is like around roughly 10% between simulation, so ground truth, and what you predicted. Of course, the model, the simulated data that you have is also like error prone, I would say, because it's a model, of course. And how big was the difference then between like validated values in real life and the deep learning part?
Yeah, that's a really good question. And that's also something that I didn't think about in the beginning, because you go like, okay, well, this is the simulation and we try to get as close there as possible using our machine learning approach. But as you said, the goal is to cover reality as best as possible and not the simulation. So what we did, we used these, they're like in CFD, there are these standard test cases. For instance, there are analytical solutions to the Navier-Stokes equations that you can use basically to validate how well your model approximates the ground truth when we assume that ground truth is the Navier-Stokes equations perfectly solved, like analytically solved and not numerically. So there are these test cases. For instance, we used this one cylinder that is like 3D cylinder that is placed in the simulation domain, where you can basically get the drag value of this cylinder in terms of the fluid properties, and measured how well first the simulation approximates this test case and also the machine learning approach. And luckily, or like how do you say, we found out luckily that the open foam setup that we used to approximate the reality of fluid flow worked in this case pretty well. So we got, I don't know, plus minus 1% accuracy in terms of how well the most important metrics are being calculated using open foam. And again, we got like plus minus 10% in terms of the accuracy of the neural net, trying to predict how the fluid flows around this cylinder. But again, as you said, these are also pretty simple test cases, and it gets more and more complicated the more complex your fluid flow is. So for instance, this might have been another question of yours regarding turbulence, which is a notoriously hard problem in CFD. We didn't cover turbulent flow because we believe that basically the neural net might be able to predict laminar flow pretty well, but we didn't try out how well it generalizes to turbulent flow. This has obviously the reasons that turbulent flow is even more complicated than laminar flow in terms of the flow field that is being generated, and also you have other values that you try to calculate using your, depending on the turbulence model that you use. I mean, you can theoretically use a direct numerical simulation to resolve every single small eddy and whirl in the simulation domain when you don't want to use a turbulence model, but obviously this would make the whole simulation aspect pretty compute intense, because you would have to have a super small simulation grid. And as I said, you need to generate many samples using your simulator in order to have enough samples that the neural network can pick up the pattern from the noise, basically. Because it's complicated, like when the fluid flow becomes more complicated, for instance, in the case of turbulence that is present, then you need even more like orders of magnitude of more samples than you would need otherwise if you only want to calculate laminar flow.
Got it. Could you maybe walk us through the steps? Like you have these typical 3 steps, right? Pre-processing, processing, and post-processing. Could you walk us maybe through how was the pre-processing like when you generated the geometries randomly, and then from there we move on to processing, how you did it there, and then to post-processing?
Yeah, sure. Okay. So maybe we start by describing how the geometries are being generated. As I said, I used really super simple shapes for these geometries. So what I did, I just made a small polygon generator that like randomly samples points in a 2D or 3D area and connect them to some kind of polygon, and then also smoothen the edges a little bit so that you don't have these sharp corners, which are sometimes also hard to simulate and can make things tricky when you try to put them into open foam. So what we did, we smoothed out every edge and corner so that we have a kind of smooth shape. And this was put into the VTK library, which can be then used to convert those geometries into open foam compatible shapes. Open foam compatible polygons. And we also did rasterize the geometry so that we could put the geometry as an input into the neural net. So maybe to quickly describe how the geometries are being represented to the neural net, they are basically being binarized into a grid. So you go through each grid cell and you look if there is a solid in this grid cell or not. And you go like this through every grid cell. So you get a binary grid containing all the values. obviously you have to select a grid size, so you can't make this infinitely large, of course. So in this case, we use something like 300 by 400 pixels and like grid cells, and these can be interpreted as pixels, which can then be put into some standard neural network architecture that have been around for much longer time for image processing, for stuff like object detection, and also semantic segmentation, which is basically how we interpreted the problem itself. It's basically like semantic segmentation, only that you don't try to predict the classes of pixels that you put into your architecture, but rather the velocities of the fluid flow that you try to predict. So this is basically the rough overview of how we did the pre-processing. The main processing was basically also another script. So it's like a lot of scripts glued together. It's a lot of glue code. So these scripts then would call OpenFOAM using the input geometry, and also a file that contains like the boundary conditions. So as you know, like you need some kind of definition of like how, like where the fluid flows into the simulation domain, where it flows out, what are the boundary conditions at every surface. So this was also done programmatically. So we also wanted to make things simple. So we used the same boundary conditions for every polygon that we generated. So it was a pretty straightforward way of describing the input to OpenFOAM. And then we would simulate the case using some fixed number of time steps, also pretty simple. And maybe like getting back to the point you mentioned earlier. So this is also a point where you could try to improve the final results by just letting the simulation run longer, so that you might have a closer view on like a better approximation of reality than what was the case for this simulation setup. Because in theory, you would have to run every single simulation forever until your solver finally converges on the actual result, which obviously can never be done. So this is also a compromise, and we use some pretty small number of time steps to keep the number of the time that every single simulation run needs to run really small, so that we could generate a couple of hundreds and a couple of thousands of simulation cases. So this is basically the main processing aspect of what had to be done for the work. And like in post-processing, we would then take the OpenFOAM results and convert them back into VTK compatible format, which is like basically saying, okay, we take this OpenFOAM output and generate this vector field out of it and remove everything that's not necessary for the neural network. So then we would have basically two images, one image containing the fluid flow in X direction and the other one containing the fluid flow in Y direction. So it's basically like a two-channel image, each of them containing for a single pixel the actual fluid vector that is was calculated at this precise location. And this also, again, allows us to put the output from this simulation case and use it as the ground truth for the network, so that it would be able to learn, okay, well, we see, okay, there's this shape at this position, so maybe the fluid flows around like this, and the network compares it with the actual ground truth. And we hoped that the network would eventually learn how fluid can flow around obstacles and through holes and stuff like that.
Mm-hmm. Yeah. Got it. Super interesting, Jannik. How was it when you shot the images through the network? Which framework did you use, and is it working like actual face detection, quote unquote?
So we used Keras, the Keras library, which was pretty new at the time and was really convenient for our work because, again, we obviously stood on shoulders of giants and used a lot of code that was already there so that we wouldn't have to implement everything from scratch. So basically what we did, we used a UNet-like architecture. So UNet is basically one of the first architectures that was invented for the problem of semantic segmentation. So as I mentioned previously, the problem of semantic segmentation is you have an image and you try to predict the class, like the semantic label for each of the pixels in the image so that you gain a understanding of a scene. So typically what you would do in autonomous driving, for instance, you would take an image from a camera that is mounted on a car. And once you have a network that is trained to solve this task, you would be able to predict for every single pixel in the image what what predicted class might be there at this position. And using this information, you can further put this as an input into another planning algorithm. For instance, when you have road detection, you know which pixels are road, and then you know where you can drive and where you cannot drive. So we use this kind of architecture also for this task because it's, when you look at it in terms of the data format, you have as an input as an image and your output is also an image, and you try to find the correspondence between what the image looks like from what the raw image looks like, what the raw pixels look like, and then try to predict, okay, what's happening at these locations. And we used, again, this UNet architecture, which was proposed three years previously. So there were already implementations out there using this architecture. So that was also pretty convenient. And we also used residual connections. So the idea of residual connections is basically, instead of trying to learn a mapping of input to output from scratch, you first approximate the output by using the identity, which is basically saying, okay, you put the same value out that you got in, and then try to estimate how wrong, how much off you are from this identity mapping, which is usually way better than trying to predict the output only from the input using no identity mappings. So this was also a speed up for our training because as has been shown in the literature, it's much more efficient and you also need less number of parameters for your neural network, which is also helpful if you don't want to overfit, which you usually do not want if your network should be deployed in a setting where it doesn't see samples that it didn't see.
Yes, and in terms of bottlenecks, you mentioned the overfitting. So are there any other bottlenecks where you said, if I would have known that in the beginning to take care of that, I would have been faster in my work?
Okay, sure. I mean, I think that's like the typical case when you try to do something that hasn't really been well established, you make a lot of things wrong. And so that was also the case for me. So I don't know, for instance, first, I actually tried to use a turbulence model and tried to predict all the small eddies and stuff like that for the model, as training data, and tried to do a really sophisticated version of what came out in the end. And I failed to generate enough training samples because it just took forever, even using a lot of hardware. And so this was one mistake that in hindsight, it was obvious that it might have been a bad idea to start with this. So maybe as a general advice, try to find the simplest version of your problem and try to solve that one before you head to the more sophisticated version of the problem, which is kind of obvious when you say it, but it's you always have to remind yourself that this is usually the case, and you shouldn't try to start with the most sophisticated version of your problem and your approach. Yeah, so that was one aspect. Another aspect was that so in the beginning I had really even simpler geometries. So this is maybe going the other way around, saying okay, I tried to to train this model using only like triangles and circles or stuff like that. So like elementary shapes and not like general polygons. And when I try to like, then I trained this model on like randomly generated circles and like triangles. So on the training set, it worked really well. But then when I tried some real world samples, like for instance, this airfoil, which is like the 2D slice of an airplane wing, it pretty much failed really bad because, again, obvious in hindsight, it didn't see these kinds of shapes in training, and it's super easy to overfit on like those simple shapes because the relationship between for instance, a circle, like when you estimate the fluid flow around a circle in 2D, it's a pretty simple pattern that arises usually, unless like you have like a Kalman eddy behind it. But if that is not the case, if the Reynolds number is different, then you would have a pretty simple fluid flow around this obstacle, and your network only learns from the data it sees, and when it doesn't see the kind of complex pattern that can arise when you, for instance, try to calculate the flow around an airfoil, then it would never be able to generalize this well to more complicated data.
Got it.
So, yeah, so that is like one more lesson that was learned in the process. Yeah, and maybe also as another thing, I underestimated the sheer number of simulations you have to run for the network to actually learn to let the network learn the difference between what's the pattern, what's the underlying structure of how fluid flow can be, how fluid flow arises around obstacles, and the like random noise that happens all the time when you put data into some machine learning algorithm. So in the beginning, we had way too few samples, which also led to the fact that we were overfitting and we weren't able to generalize to other shapes.
Yeah. Okay, that's super interesting, Jannik. What I wanted to ask, of course, is the physics. So we know from our lectures in fluid mechanics we had together, and also in our master's lectures, you know, this kind of divergence theorem where it says divergence of the velocity field equals 0 for incompressible fluid flow, of course. Can it be proven that it still exists, like this condition exists in the deep learning framework? Things like the mass continuity and continuity of energy, for example, in a compressible case.
Yeah, that's also a really interesting and good question. We also investigated this. So this also goes back to how we can measure the error of the neural network prediction. In this case, as you said, in a non-compressible fluid, you would have a divergence that is everywhere 0 in the fluid flow field. And the interesting fact is that even though we did not explicitly tell the model that this should always be the case, so what you could have done in this case would be to say, okay, we have not only the loss function that says try to approximate this simulation output as closely as possible, but you could also have said, okay, now take this output tensor that the model spits out and put this other loss on top of it, not only saying try to approximate the simulation as close as possible, but also say, okay, let please be this divergence always and everywhere be 0 in your output. And then the model would basically be forced to apply this constraint and to adjust its predictions accordingly. In this case, we didn't explicitly model this, but we found out later that implicitly this was actually modeled as well. So what we did, as we knew that for incompressible flow, the divergence would everywhere be 0, and we only had as a like as a condition for the simulation that the flow, that the flow is incompressible. So we knew that this should always be 0 for every pixel in our image. And we found that it's really well approximated. So more or less, like obviously you have some divergence, but basically it's more or less 0 everywhere. This again tells us that you don't always need to explicitly say something in order for the model to learn it, but it comes like as a side effect of the data you put into it. Maybe to phrase this a little bit clearer, obviously the model has no intuition whatsoever about the physics behind it, so you wouldn't be able to like use it to do explicit calculations of any kind. So this the idea is not to have a model that can like implicitly learn all the physics that's out there. I mean, this would be pretty amazing, but that's unfortunately not the case yet. But the idea was how data itself can allow a machine learning algorithm to approximate what explicit calculations give as an information. So basically, we try to find out, okay, the data itself is consistent because for every sample that we put into the model, the divergence is everywhere 0. And this should lead to the fact that once the model has learned something out of the data, that it's able to make predictions that are like in the same, like out of the same class as the input that we put into the model during training. And we found that this is the case for like most shapes and most random polygons that we put in there. But obviously, again, once you use different distributions from which you sample those simple shapes, you get into areas where the predictions are pretty bad and like the drag values are off and the divergence is non-zero for like with orders of magnitude larger than what would usually be the case. So you pretty soon hit limits once you use samples that are not out of the distribution that were put in during training.
Mm-hmm. Got it. So to wrap things up, so we're now closing this beautiful topic of CFD plus deep learning. And if you want to have more information, I'll put links from Jannik that he provided us with in the description. You also mentioned that you work in robotics. Now there's this beautiful example, of course, from OpenAI where they use dexterity to solve this Rubik's Cube, which I'm also a big fan of. Mm-hmm. Where do you see robotics using deep learning and also deep reinforcement learning is going into the future? And how do you personally use these kind of techniques during your work or for your work?
Okay, so yeah, deep learning has led to amazing results. You mentioned dexterity. I mean, there are like so many examples where amazing companies put out really nice demos and products using deep learning for the last at least 5 years. I mean, the deep learning revolution is already almost 10 years old now. So amazing things have started, like amazing things have arisen from this revolution. And robotics is also part of this. What makes things super interesting in robotics is that you have like, you have to mess around in the real world. So maybe people are not always aware of this, but the reality of like being outside or like navigating through any kind of environment, it's like super messy. You have so many sensory input data, you have so many modalities like sound and vision and tactile feedback. And we as humans have evolved to deal with this kind of data, because obviously it can be interpreted as data, to deal with this kind of data really well. And we can easily, like even as a small child, we really soon learn how to navigate in this complex environment. And what robotics in particular has struggled with for many, many years is that basically you cannot model the real world as close as you would like in order to develop algorithms that allow autonomous robots to operate in this kind of messy world. And what deep learning has really helped us is to gain an understanding of how we can perceive our environment using these deep learning models, and also how to act within them. So the basic idea, like the main mantra had been that you have to explicitly model everything that's out there, basically. So you would have a sophisticated algorithm programmed by humans trying to predict every single small edge case of stuff that could go wrong or could be somewhere around the robot, and make the robot act and perceive the stuff accordingly. And as was the same idea in like symbolic AI and like the early AI projects where you were where people tried to explicitly model every kind of information that's out there. Obviously, this approach had its limits, and these limits were hit like really often. And what deep learning has helped robotics is to allow to generate models that are not explicitly that don't try to explicitly model the environment, but rather only model how the information, like the important part of the input, arises from the raw input itself. Basically, again, trying to pick out the relevant information from all the noise that's out there. So, for instance, a typical example would be like perception systems on autonomous vehicles. As you mentioned in the beginning, you would have like face detection or object detection on images or on all other kind of data, for instance, point clouds. And back in the day, algorithms weren't able to like handle these kinds of images and point clouds if you didn't model everything explicitly and made a huge algorithm that was really slow and also didn't cover a lot of edge cases, because there are basically infinitely many edge cases that you would need to cover. And these deep learning algorithms really helped robotics to perceive the environment in a way that allows them to use the relevant information for their own goods, for their own means, which is to, for instance, navigate from point A to point B, not making an accident and not hitting any pedestrians or stuff like that, which sounds simple to a human, but is really a really tough problem for autonomous vehicles if we stay at this image. And one what we as like researchers try to do in the future, and you mentioned, for instance, also deep reinforcement learning, which is also something that came up kind of recently. I mean, we had reinforcement learning ages ago, but deep reinforcement learning using neural nets is kind of a new thing that started only a couple of years ago. And robotics really benefits from the opportunities that deep learning models give us, both in terms of perceiving the environment, which is again like perception, trying to find out where is stuff, and also reinforcement learning and similar approaches like inverse reinforcement learning or imitation learning, where you try to imitate the behavior of, for instance, actual humans and try to learn how they act in their environment, depending on what their environment looks like. These kinds of approaches allow us to build way more robust and also way more safe models for autonomous navigation and autonomous perception. And in the future, I expect obviously the deep learning revolution to continue, even more so when we have more data, because this is like, basically this is the most important ingredient for any deep learning model, is that you have enough data, and there is no enough data. Basically, there's only more is better. So in the future, I really hope that robotics will be like also like navigation-wise and also perception-wise, to be able to use the data that these platforms give you using cameras and other kinds of sensors to have enough data so that you can use these models even better.
Mm-hmm. That sounds. I'm very thrilled to see what happens in the future. I think you do as well. Talking about the future, do you think AGI systems will be there soon? Whatever soon means.
Mm-hmm. Yeah, sure. I will put in any number I like, because it's always like 10 years or 20 years in the future, no matter when you talk about it. So might be the case here as well, like in year 2020. But to be perfectly honest, looking at the way we do research in deep learning right now, we don't see in the foreseeable future, we don't see an approach that might actually really lead to AGI. So what most models and most researchers work on are pretty small sub-problems of the whole problem of intelligence. Like, as I am a robotics researcher, we are trying to look at how we can perceive the environment as best as possible and act in it as best and as safe as possible. However, AGI entails many more tasks that we don't even have any kind of benchmark for yet. So for instance, a super interesting topic is like intuition, is like basically, or common sense, which isn't even taught at schools or anywhere, because as the name says, it's common sense. You know it based on your experience that you make in the world. So there's like no class on you shouldn't touch the oven if it's hot or anything. But this is exactly the case for systems that we are building right now for robotics, or like machine learning and deep learning models in general. You try to bring up and have as many samples as you can, saying, okay, well, this is good, this is bad. This, I don't know, when you describe how a zebra looks like, it tries to learn based on examples of what a zebra looks like, that when it sees a new one, that it can detect it. However, at least we as humans, and we humans are the only intelligent, like on that level, intelligent species that we know. So this is like our only sample out of the intelligence distribution that is interesting to us. So we try to orient on the way we humans learn stuff. And as I said, for common sense and like this intuition topic, we didn't find a way yet to describe reality for a machine in a way that it can actually learn intuition and learn how it can use this intuition and this common sense to solve most problems that it encounters. Because we as humans, it's super easy for us to say, okay, we basically learn on the fly, even without any labels. We don't need any supervision in any way to learn this kind of intuitive knowledge. For instance, when we learn that, okay, an apple falls from the tree because of gravity, you would know that when you hold up a banana, it would also fall, obviously. I mean, I can't even describe why we know that, but I mean, we can generalize from one example in this case to infinitely many, unless like the thing is lighter than air and stuff. But these are like edge cases that we can also pick up, maybe in a physics class, but the most easy ones we can pick up basically instantly. And in the case of a machine, it wouldn't from the start know that, okay, when you hold this different kind of object up, it would also fall. You would have to say, okay, if I hold a banana up, it falls. If I hold a glass of water up, it falls down. Stuff like that. Yeah, it's obvious to us, but this is the kind of data neural network sees today when you try to make it learn about something, for instance, I don't know, object detection or something. So it learns eventually, but this kind of intuition that people have and we all grow up learning, is something we have a hard time trying to put into autonomous machines and deep learning systems, or like machine learning systems in general. So to come back to your question, I can't even, like, it might be as well 100 years or something, because right now, at least the way we do research right now tries to solve like small subtasks, but even when you put together all the models that have been ever trained on any kind of problem, you would still have like a neglectable fraction of the kinds of problems that you have to solve on a daily basis when you are a human being. So in order to make the models generalize better and to like so many edge cases that are out there, I believe we might need a different kind of approach altogether, trying to actually build AGI systems again. But the way we do research right now tries not to tackle this problem as a whole, but to pick like the small things that we hope that a machine might be able to do, but not the whole picture.
I think even from finite element method or CFD, this whole divide and conquer approach applies also here, that you take small subtasks, use brilliant minds like yourself and work on these hard problems, and then successively build your way up towards AGI whenever that is. But I think a perfect sentence here is like that we underestimate what we can achieve in a month, but overestimate what we can achieve in a month, but underestimate what we can achieve in a year, so to speak.
Yeah.
Exactly. Yeah. And last question, which is a bit tricky. So assuming that AGI will be there in, like, let's say 1 or 2 years, like hypothetically, what would you ask this AGI system if you could talk to it?
I would, okay, maybe this is like cheating or like a cheap question to it, but I would actually ask exactly this kind of these kinds of questions that we just talked about, this kind of common sense, this intuition thing. I would ask it, how do you know that this and that is true? To make it show that it can reason about the reality, that it's not only able to pick up from examples like machine learning algorithms today would do, but rather find out if it can actually think the way we can think when you define thinking as like reasoning from A to B and then from B to C, and make the connection between A and C without seeing like a million examples of how this is done. This would like really impress me. And I mean, we don't know how an AGI system might reason, because again, humans are the only species we know of that we can talk to and ask how they reason. So the most interesting question to me would be, how does an AGI system reason when we don't explicitly teach it how to reason, which would be obviously our goal, because then it would kind of also not be AGI, but only like mimic us in a way that doesn't really represent intelligence.
That's a beautiful answer. Jannik, with that being said, I would wrap things up, and I would like to thank you so much for your time, for this beautiful insight to CFD using deep learning, but also a bit of robotics, and your beautiful and well elaborated answers towards these kind of topics. Thank you so much, and hopefully there will be a second session talking more about robotics then in the future.
Yeah, I would love to. Thank you very much for having me.
Bye-bye.
Bye-bye.